Hello everybody, this is Unit 7 Progress Check FRQ Part A. A calculator is not allowed on this problem, which is kind of fun. Okay, so all we're going to do here is it says the population of a virus host excuse me, can be modeled by the function that satisfies the differential equation, which is just the derivative of A, t minus 1/5 of A. This is interesting because this is not separable because there's a t right there and an a right there, where a is measured in millions of virus cells and t is measured in days from 5 to 10. At 5 days, there's 10 million cells of the virus in the host, which is interesting. So we know that at a at 5, when the time is 5 days, there are 10. So that's interesting. So we know a of 5 is 10. Okay, so write an equation for the line tangent to the graph at A at time 5. Use the tangent line to approximate the number of virus cells in the host in millions at 7. Okay, so I need my derivative at 5. But in order to do that, according to this equation, dA dt is t minus 1/5 of A. So I need the time and the amount, which I have, because at time 5, my amount is 10. So 5 minus 2 is 3. Now this is important because now I know that my line equation is y minus my y value equals my slope, which is now 3, t minus 5. So there's like my line equation, right? My tangent line equation, but then I'm supposed to use that to estimate the number of virus cells at time 7. So I'm going to solve for y simultaneously, adding 10 to both sides, while I stick in my 7, and I've got 10 plus 3 2's, which is 10 plus 6, which is 16. Approximate the number of cells, 16 million cells. Okay, so this is part A. That was not bad. Okay, part B. Show that, show that that whole big deal right there satisfies the differential equation. That with the initial condition that A of 5 equals 10. Now, this is kind of interesting here because I know that A of 5's got to equal 10, but then my derivative of that has to equal this. It's kind of a backwardsy thing since this isn't really solvable by hand. They're saying that the derivative of this A equation better equal that. So let's find out both. First of all, let's make sure that when I stick in a 5, I actually do get 10. So I'm going to go negative 25 plus 5 5's plus 10 e to the, now this is kind of cool because the negative 5/5, which is negative 1, plus the 1 will be e to the 0. So negative 25 plus 25 plus 10 times 1, e to the 0, 1. So I've got 0 plus 10, which is 10. Check. Okay, now my derivative of that better equal this deal. So dA dt is going to equal, now I'm pointing at the different things I'm taking the derivative of. That's going to be 0. That part's going to be 5 with respect to t, plus 10 times. Now the derivative of e to the something, this is chain rule, is e to the something times the derivative of the exponent, which is negative 1/5. Okay, that's everything there, right? Which is good. Okay. So now what I've got to do is figure out, let's simplify this a little bit. 5 minus 2 e to the negative t fifths plus 1. Now we got to figure out if that's this. Is this that I just got the same as this, which was given? Well, maybe instead of manipulating this, I'll just go up here and ask it and say, hey, are you t minus 1/5 of the thing that we started with? which is negative 25 plus 5t plus 10e to the negative t fifths plus 1. Hoping. T my, now I'm going to distribute in this negative 1/5 of the negative 25, which is plus, 5, 25 fifths, 5. Beep. And then negative 1/5 of 5 is negative 1t. Ooh, those are going to go away. Negative 1/5 of 10 is negative 2e to the negative t fifths plus 1. The t's are going to cancel out. And I've got 5 minus 2e to the... Hey! That is the same as that. We did it. Yay. Okay, so the next thing we need to do is... This is a really interesting part. It says I need to show the model by the host receives antiviral medication. The amount of medication is modeled by M that satisfies this, where M is measured in milligrams, T is measured in days, K is a positive constant. If the amount of medication is 30 milligrams at time 0 and 15 milligrams at time 3, what is M in terms of T? This is really interesting. Okay, so I'm going to have to do this solving equation here. You notice here, dmdt, let me get rid of all that. dmdt, I'm going to have to travel around the page here a little bit. dmdt is negative 1/2 of that. So if I bring the M over to the M side, and I leave all this business over there, I'm going to leave the half over here. I'm going to go 1 over M with the dm. I'm separating a differential equation, equals negative 1/2 of, okay, 1 over t plus k dt. Now k is a constant, so now I'm just going to integrate both sides. And the integral of 1 over m with respect to m is ln of absolute value of m. I don't think we're going to need the negative because my m is an amount of a positive amount of medication, okay? And then my integral over here, I'm going to pretend to pull that negative 1/2 out, is ln of the absolute value of t plus k plus c. Now this is interesting because we know, well, I guess we could, let's see. What if we stick in 0, 30? Let's try that. ln of 30 equals negative 1/2 of ln of k plus c, but I still don't know k or c. Well, let's try the other one. 315. Oh, geez. So ln of 15 equals negative 1/2 ln of 3 plus k plus c. So I guess I could solve both of these for c to solve for k. This is kind of complicated. All right, here we go. So I'm going to solve both these for c. This one is ln of 30 plus 1/2 of ln k. That's c. That's c. Oh, but they're not the same c. Same k. Oh, geez. Well, let's think about this for a minute. If we've got this guy right here, a couple different things. What if I call this ln of m equaling, now let's bring this bad boy up here as an ln of, now t is going to be positive and k is going to be positive, so I think I can get rid of these absolute values. Okay, so we're going to go t plus k to the negative a half, but I still have the plus c over here. Okay. But what I guess I could do is I'm trying to get the ln gone, so maybe I can call that c, like an ln of something else. I'll stay consistent with what they're doing there. I'll call this a d. ln of some d is the constant c. This is weird. Okay. So now ln of m is ln of 1 over root t plus k plus the ln of d. But remember, ln of adding is the same as the multiplying of the arguments, so that's ln of d over root t plus k. Okay, that was not intuitive. But since ln of this equals ln of this, that means that m equals d over root t plus k. Okay, I'm going to pull in some extra paper here. Reserve paper. Okay, so what that means, since m, let's see that okay? Yeah, since m equals d over root t plus k, now I'm going to use my 2 points. I'm going to use the point 0, 30 and my point 315 to try to solve for stuff. All right, let's figure out where we are here. So if I stick in 0, 30, then this is tm, 30 equals d over root 0 plus k. So 30 is d over root k. 315, 15, so that was that guy. This is this guy. 15 equals d over root 3 plus k. So far, so good. So from this guy, d is 30 root k. And from this guy, sorry for my improper continuing notation here, d is 15 root 3 plus k. So now I'm just going to solve this guy. So that means 2 dividing both sides by 15, 2 root k equals root 3 plus k. All right. So I'm going to square both sides and see what happens here. So that means that 3k equals 3, k equals 1? K equals 1. Okay, I guess so. K equals 1. All right, that's good. So k equals 1. That means that m is equal to, oh, well, if k equals 1 and d is 30 root 1, 30, or 15 root 4, which is 2, 30. So I guess d is 30. So m is 30 over root t plus 1, which was the k. Oh, my Lanta. That was a little bit tricksy. Okay, well, there it is. There's parts A, part B, part C. Ran into a little hiccup there on part C. If you guys can figure out a simpler way to solve for that for me, that would be great. But there is Unit 7 FRQA number 1, no calculator. All right.